like to speak here to the organizers and more generally to the organizers of this broad event, which has already been beneficial, as you will see also in a bit. So what I'm going to talk about in this talk today is a joint work with Salma, which appeared a few weeks ago in the Journal of Algebra. So whenever I talk about some result, unless stated otherwise, it comes from there, or to a large extent also from my PhD thesis. Okay, so let me start by giving the setting. These are all objects that most of you certainly know very well, but just to set my notation, I will be talking about Hahn fields mostly. And Hahn field is a field, well, the maximal Hahn field, what I am, is it right? What I am denoting by this boldface K, or K double brackets G, where little k is any field and G is a totally ordered abelian group. I call the maximal Hahn field, and is the field of generalized power series with exponents in G, where the support of a power series is well ordered. The operations are defined in the usual way, term-wise addition and convolution multiplication, and it's a classical result of Hahn that this set with these operations is in fact a field. And it always contains the group ring consisting of the fields of the elements with finite support and the fraction field thereof, so the function field of K over G. And for me, a Hahn field, and throughout this talk, a Hahn field K will just be any field which is comprised between this function field and the maximal Hahn field. All right, so some very usual examples. If I take G equal to Z, I can take the function field in one variable. Those are the classical Laurent series. Sorry, the KZ, or if I take K double brackets Z, those are the classical Laurent series. Those are examples of one minimal and one maximal Hahn fields. Or if I take G equal to Q, I can consider the Puiseux series, which gives an example of a Hahn field which is neither maximal nor minimal. And over Hahn fields, we can define in a canonical way a valuation by taking the minimum of the support, and for non-zero power series, of course, mapping 0 to infinity. And just to set again some of the notation that I use, these are the valuation invariants that come attached to the valuation, right? So the valuation ring, oh, I always get the wrong button, valuation ring, valuation ideal, the 1 units, so the group of units, which is just 1 units times K, and we can canonically identify the residue field with little k via this canonical map, right? Just mapping every element in Rk to its zero coefficient, to its coefficient at 0. Okay, so what I want to look at are automorphism groups. So mainly, I will be looking at the groups of valuation preserving automorphisms of a Hahn field case, right? Meaning those automorphisms of K such that whenever two elements have the same value, then also the images have the same value. And some subgroups of this group that I'm interested in are what I will call the K-stable automorphisms, namely those automorphisms that fix little k setwise, and the K automorphism, which instead fix K pointwise. Okay, right. So to motivate a bit the work, I want to quickly recall a result of Kaplansky. So if I take a valued field now, general valued field, and if I want to study the group of valuation preserving automorphism of a general valued field, say F with valuation W, if I assume that this valued field admits sections, right, for both the value group and the residue field, so that I can embed the residue field into the field and the value group into the multiplicative group of the field. Then there is a classical by now result of Kaplansky that says that under these conditions and some other condition, and something needs to be taken care of for characteristics and so on, factor sets. But the moral is that I can embed my valued field into, in a valuation preserving way, into the Hahn field that I obtain by taking the residue field and the value group with the canonical valuation. And also in such a way that I can embed the function field into this image. So the moral is every or almost every valued field is isomorphic in a valuation preserving way to a Hahn field with its canonical valuation. And that's why we study the valuation preserving automorphisms for Hahn fields, right? So this is what we want to study. And how do we do that? So what I want to do is I want to describe the groups of valuation preserving automorphisms of a Hahn field K in terms of the automorphism groups and more of its valuation invariants, right? So the automorphism groups of the residue field, the value group, the one units, and this and more that I wrote here comes from the fact that I will also look at homomorphisms between these objects. And the strategy to do this is to use natural maps, so maps that I can define in some natural way from my automorphism group into these groups of automorphisms of the valuation invariants, and study these maps. So studying the kernel, whether they have sections and the images of the sections in order to obtain decompositions of this group V odd K. So let us see how this is done. So first of all, before I define the first map, I want to mention that automorphisms, valuation preserving automorphisms can be characterized in many ways. Among others, so Salma, Michele, and Françoise Point showed a criterion. They actually did it for general valued field. I'm presenting here a bit of it just for Hahn fields, that an automorphism is valuation preserving if and only if these two induced maps are well-defined automorphisms. So the map sigma G, from G to G, mapping the value of something onto the value of the image, is an order-preserving automorphism of G. So this is my notation for order-preserving automorphism. And similarly, the induced map on K that I obtain by mapping an element of K to the coefficient at 0 of its image, I'm identifying alpha with alpha times t to the 0, is also an automorphism of little k, right? So to every valuation preserving automorphism, I can associate these two automorphisms. And here comes the first map that I want to use. So phi k is precisely the map from V odd k to the product, automorphisms of k times order preserving automorphisms of G, mapping sigma to the pair sigma k, sigma G, right? And the first thing I do is I give a name to the kernel of this map. So those automorphisms that induce identity via this map, both on K and on G, I call the internal automorphisms, right? And I call, and I denote the group by int odd K. So clearly, being the kernel of a map, this is a normal subgroup. And I can also describe this group as the group of those automorphisms that fix the valuation, right? So not only they are valuation preserving, they are valuation fixing, and that fix the first coefficient of every element in the valuation ring, the coefficient at 0. All right, so this gives me a first subgroup, right? So I am identifying a subgroup of V odd k. In order to obtain a decomposition, then I want a complement to this subgroup. So to get this complement, I need to assume something, right? I need to assume that my field K satisfy what I'm going to call a lifting property, right? So if the map phi K that I've just defined admits a section, right, the right inverse, so an injective map from this product into V odd K, which if I compose in this order gives me the identity on this product, then I say that the field K has the first lifting property, right? Examples of fields that satisfy this property and some other will come in a bit. And now that I have this, then I can use a, well, first of all, I have an injective map that now goes from odd K times odd G to V odd K. So I can give a name to the image of this map. And I call this image the group of external automorphisms. And of course, because the map is injective, the external automorphisms are always isomorphic as a group to that product. But what happens is now that I have an exact sequence, right? If I look at this map here, I can, up here, I can embed the internal automorphisms into V odd K, and that gives me an exact sequence. And if I have the first lifting property, that exact sequence splits, right? I have an inverse there. And I know by general group theory that then the group in the middle, V odd K, will be isomorphic to the semi-direct product of the inward mappings. And this is exactly what I get here, right? If I have the first lifting property, then we can split the group of valuation preserving automorphisms into this semi-direct product. And as you see, we have, in the spirit that I have announced at the beginning, we have described at least part of this group in terms of the groups of automorphisms of two-order valuation invariants. So the goal now is to continue go in the same spirit and apply basically the same procedure to the internal automorphisms. Before doing that, though, I want to mention now here you see that the first lifting property essentially seems to depend on the choice of a section. So first of all, I want to give you a special section that one can choose. So, and I'm giving it at the beginning on the maximal Hahn field, okay? So for the maximal Hahn field, whenever I have two automorphisms, rho and tau, rho an automorphism of K, tau an automorphism of G, then I can always choose this canonical section. So mapping the pair rho tau to the automorphism that acts in this way. I just let rho act singularly on coefficients and tau act singularly on exponents, right? This is what I call the canonical section on the maximal Hahn field, which therefore has the first lifting property, and it has the canonical first lifting property according to this definition. So a general Hahn field K has the canonical lifting property if and only if it is stable under this automorphism of BK. And again, examples and non-examples of fields satisfying this will come in a bit. All right, so yeah, so we were here, and like I said, I wanted to go on and apply this idea also to this, to the second factor, right? To the first factor here, which I haven't described in terms of the valuation invariance. So I want to notice just that it's apparent here why is it called lifting property, because I'm lifting automorphisms of K and G to automorphisms of of K. And now what I want to lift with the second lifting property that I am about to define, instead I want to lift homomorphism between G and K, two automorphisms of K. So step by step, I get a natural map, which I'm calling now XK, from the internal automorphisms this time into the homomorphisms from G to K star. I'm taking pointwise addition in the homomorphism group. And this map is given by mapping sigma to X sigma, where X sigma is the homomorphism that maps G to the Gth coefficient of sigma of T to the G, right? So T to the G has value G, sigma is internal, so it fixes valuation. So sigma T to the G also has value G, so I can take its Gth coefficient. And I am using this notation here, X to the G, because I really want to interpret those in a second as exponentiations, right? So raising constants in a sense to powers that come from G. So again, I look again first at the kernel of this homomorphism, and I call this kernel the group of one automorphisms of K. And this can be described as the set of automorphism, valuation preserving automorphism, that are actually, again, valuation fixing, and then that not only fix the leading coefficient of some power series, they fix the leading coefficient of every power series, wherever the leading coefficient might be. Obviously, again, this is a normal subgroup, and we do the same, we play the same game as we did before. So I say that K has the second lifting property if this map that I just defined admits a section. Now the section I'm going to call, it looks like a P, it's a row for me, a capital row, row K. And if I have the second lifting property, then I look at the image of this map, which I call, in fact, the G exponentiations for the reason that I said just before. And again, because of the same group theoretic game that I did to pass from V automorphism into the first decomposition, then I can decompose the internal automorphisms into this semi-direct product. Again, because I'm taking the image of an injective map, the G exponentiations are, as a group, isomorphic to the homomorphisms between G and K star. And this gives me now this second level of the composition, right? So now I have a four-factor product where the last three factors are described purely in terms of the valuation invariance of K, assuming that I have, of course, the lifting properties that I require. And here again, I can define a canonical version of the lifting property, namely given, and I do it first on the maximal Hahn field, Blackboard ball K, where I take any homomorphism from G into K star, and I associate to it the automorphism of K that is given by decorating a power series here by multiplying each term by the image of the relevant G through X. And if you want, this can be seen also as an analogous of substitution, of composition of power series, right? We know that we can do that in the field of Laurent series, for example. It's ensured by Neumann's lemma that one can do that not just for constants, even for more, and we will also do it for something more later, that we can replace T by T multiplied by some suitable series. And this is the next thing to it, right? This here we can imagine more or less to be replacing T by t times x. T times x doesn't really have a meaning, but the moral is that thing is the next closest thing to composition of series in that sense. Right, and yes, so again, as before, if a general Hahn field K is stable or closed under this automorphisms of BK, then we say that K has the canonical second lifting property. Okay, so I gave you these two lifting properties, what they are good for, and I promised you that I would at least justify the fact that I'm not talking only about the maximal Hahn field, that there is a sufficient supply of Hahn fields that satisfy these lifting properties. And yeah, I gave a talk in this broad program in March, I think, where I focused extensively on Rayner fields. I'm not assuming any of you to have been there or to remember that, but so Rayner fields are special Hahn fields that one can obtain by taking a family of subsets of G that satisfy a bunch of conditions, right? They have to be well-ordered subsets and they have to satisfy some more conditions. I will not go over them now, but by a theorem of Rayner, if a family of supports satisfies this condition, then if I take all the power series that have those supports, which I'm denoting by this little k double brackets f here, if I take them all, then I get again a Hahn field, right? So I get again a field. And examples again of fields that can be obtained in this way, the field of Puiseux series can be obtained in this way from by taking specific families of subsets of Q. We can obtain the so-called kappa bounded Hahn fields, right? If the field subfield of BK of elements of support of cardinality less than a given cardinal kappa. And a non-example of this is the minimal Hahn field. Now, minimal Hahn fields can be obtained as a Rayner field, right? This comes from the fact that, for example, the exponential of t to the g is not a rational function, but it has the same support as something like 1 minus t to the minus 1, which instead is a rational function, right? A Rayner field has the property that as soon as something belongs to it, then everything with the same support belongs to it as well. Whereas here we have one support is there and something else with the same support is not. Okay, and so for Rayner fields, we can prove this result. So if we have a Rayner field F, well, yeah, I'm calling F the field and F the family, sorry about that. So K of F, then all Rayner fields satisfy the second canonical lifting property. And we have a criterion here for Rayner fields that in order for them to satisfy the first lifting property, namely a Rayner field satisfies the first lifting property if and only if the family that it is determined by is stable under the action of the group of order preserving automorphism of G, right? If I take an automorphism of G, I apply it to an element of the family, then I get again an element of the family. Okay, so therefore, by this theorem, it follows that the maximal Hahn field of the kappa bounded and Puiseux series field satisfy both the first and the second, even canonical lifting property. And using that criterion that I just showed, it can be shown that some Rayner fields does not satisfy the canonical lifting property. And I want to credit this example. I mean, the idea of this example was suggested to me by Van Sambach, Yoko, and Christoph Kessling in occasion of the other talk that I gave. So again, thanks to the program. And yeah, I will not go over it. It's just to say that there are examples of that. And again, I'm stating here as non-example the minimal Hahn field, because as we saw, it is not a Rayner field yet it satisfies both canonical lifting properties. Now, something that we do not have here, it's missing in the picture, is an example of a Hahn field that does not satisfy the second lifting property. And I don't have one yet. So because see, the examples that the non-examples for the first lifting property that we have come from the criterion that I just gave. And that's because of the fact that Rayner fields are defined by conditions on supports. Right, so to get a counterexample, you have to choose a clever field and a clever family so that you get the Rayner field that violates that principle. Now, because the second lifting property instead has to do with lifting homomorphism into G exponentiation, so G exponentiation do not touch the support at all. They only shuffle the coefficients. That's why all Rayner fields satisfy the second lifting property. So there is a direction where I have hope to find counterexamples, namely defining, we are working on that, we're defining some specific Hahn fields that can be defined in a similar way to the Rayner fields, but instead of looking at conditions on supports, looking at conditions on the coefficients. Right, and that is where I have hope to find an analog to this criterion for the second lifting property, right? And to know what those fields are about, I invite you to check out Sebastian's talk on Friday. That's exactly what he's going to talk about. Okay, yes.
Are there any other lifting properties of the canonical ones?
Yes, you are way ahead of me. So, right now again, like I said, the lifting property depends on the choice of a section, right? And I gave a I don't know where I have it here. Here's one, and there are some canonical sections that one can choose. So, can I find other sections? I can definitely find other sections, and one way to find another section is start, for example, from this section or from any section you have, and conjugate by elements. Here I have the first lifting property on the slide, so conjugate by internal automorphisms, right? I take a section like that, and I fix an internal automorphism, and then I take the section that I obtain by lifting something and conjugate this something by a fixed internal automorphism. So as soon as I have a given section, I have a whole conjugacy class of sections. For the conjugacy class of the canonical section is, I don't know how interesting the whole class is, because you have everything as soon as you have one. What we're still working on is, can there be different conjugacy classes, right? So the canonical section is the one for which we have a class that we can work by hand. So a concrete example, writing down an element of a different conjugacy class, we haven't done that yet. It's something that we have in mind for the immediate future. Right, yes, so thanks. Okay. So, where was I? Right, so, okay, so this is the picture that we have up until now. So if we have both lifting properties, we can decompose the group of valuation preserving automorphisms in this way. And here I'm also giving you the decorated version for the k-stable and the k-automorphism. So interesting maybe to notice here is that in order to move to the k-stable automorphisms, I only have to decorate here with the little k, because for everything else is already k-stable. And for the one automorphism, being k-stable and being a k-automorphism is the same thing, right? So that's the first step downwards. And the second step downwards is if I want to have k-automorphisms here, again, here everything was already K automorphism, and all I have to do is I have to get rid of the odd K component here. That becomes trivial. Okay, so this is the picture up until now, but again, we want to go further in decomposing, trying to decompose the last group that we have there, which is not expressed as in terms of the valuation invariance, and that is the group of one automorphisms. So this is what we are going to attack now, right? So here again is a picture of the decomposition. The double lines here means that smaller group is normal into inside the bigger one. Okay, so moving to this factor here. So in order to attack this one, I will need to focus to have one more restriction, right? So at every step I need some more restriction, right? One lifting property, two lifting property. And the next one that I need is I need to restrict to strongly linear automorphisms in order to be able to tell something more interesting about that group. So let me give some definitions first. So first of all, I want to define summability. So a summable family of elements of K, a K-summable family of elements of K is a family A indexed by a set I with two properties that if I take the union of all the supports of members of A, I get a well-ordered subset of G. And for every element in this union of supports, every element in this union of supports only occurs in finitely many of the elements of A, right? And if a family A satisfies these conditions, then I call it K-summable, and I can take the sum of such family, namely the sum over I of all the elements of I is simply the sum over this support, and the Gth coefficient is simply given by the sum of all the Gth coefficient of those power series where G occurs in the support.
But you asked if this sum is in K.
Absolutely, yes. That is actually missing. Yeah, that it should be there. I'm required that this sum belongs to K, of course. This way, K summable, precisely. Thanks. Sorry about that. Okay, so that's the summability definition. And now comes the important definition of a strongly additive, so strongly linear automorphism. So I take a K automorphism, valuation preserving K automorphism of K, and I say that such an automorphism is strongly linear if whenever I take a summable family, then the families of the images, both under sigma and under sigma minus 1, are summable families, and this relation holds, right? So the image of the sum coincides with the sum of the images, both for sigma and for sigma minus 1. Obvious question here is whether I actually need to require the condition on both sigma and sigma minus 1. And as far as I understand, to this level of generality, for all we know, it is necessary, although there are conditions under, and quite broad condition I'm given to understand, where the statement on the condition on sigma minus 1 is implied by the condition on sigma. And for something more about that, I will refer you to Vincenzo's talk on tomorrow. I think he's going to tell you something about that too. Okay, so just to be sure that I have a group there, I am assuming both conditions here. And the group that I have here, I am denoting it by adding this, decorating it by this little plus, and that is what I call the group of strongly linear automorphisms of K. Okay, so quick remark. The external automorphisms and the G exponentiations, the way we have seen them before, they are already strongly linear. They all happen to be strongly linear. And therefore, when I look at V odd k plus from the decomposition that I had before, when I plug in the decoration, I get this decomposition here. And so we see that what we need to chase is now really this 1 odd k plus, okay? And we want to do that in the same way as with before. So the idea is, again, to try to look for a map that will allow me to play a game like I did for V odd k in the first place, 1 odd k, internal automorphisms the other time. And one natural map that I can consider on the one automorphism, this is also to explain why I am moving to the strongly linear one automorphisms, right? So there is a natural map from the one automorphism, the 1 k1 automorphisms, given by this x1 mapping sigma to this homomorphisms of G into 1 plus ik, right? So now the valuation invariant that I want to look at is 1 plus ik. And I map G onto this. I mean, I have this, it's called logarithmic derivative. So sigma map gives me the map that maps G onto sigma of t to the G over t to the G, right?
And logarithmic derivative is the name when sigma is a derivative.
Yeah.
But I was kind of trying to.
Yeah.
I guess logarithmic difference, or is there a name for this?
Oh, okay.
Let's call it logarithmic derivative.
Well, I'm happy not giving it any name. It's just to put a flag on it, you know. Right. So again, that what is in fact that's always a 1 unit, right? I mean, I always get a unit, and then I divide by t to the G, and I get a 1 as first coefficient. And the problem with this map is that it is not a group homomorphism. And so I say, okay, I don't have a group homomorphism, but I can say, well, if it was at least injective, I could say, I take the group structure that I already have on the left, and I transfer it via an injective homomorphism onto the set that I have on the right. And that's where the strongly linear subgroup comes into play. Because if I restrict to the strongly linear subgroup, I in fact get an injective map. So x1 restricted to 1 odd k plus becomes injective. Okay, and because of this, I define my set for now of summable homomorphisms of G into 1 plus ik to simply be the image of the strongly linear one automorphisms under x1. So this can also be defined in a independent way. So I can also define the summable homomorphisms of G to 1 plus ik as those homomorphisms such that for all power series sum agt to the G, this sum here is an element of K, right? So here I am implying that the family that I get out of there is summable, and that summable is an element of K. Because those psi of G are 1 units, right? And this is, again, the place where I am doing a similar thing to the substitution that you could do in the case of Laurent series, right? When you can replace T by, for example, T times any unit. Here I did it in 2 steps. I'd replaced T by T times a constant once, and then T times a 1 unit. So the analog thereof. Okay, so now, because I have that injective map, when I restrict to the image of that map, I get a bijection, clearly. And the idea here is simply to define a suitable operation on the group on the right, such that this bijection becomes, in fact, a group homomorphism, so an isomorphism of group. And the way we do this is by taking, as explained here, right? I take the units, the 1 units associated to homomorphisms sigma and tau, and I define their product to be the homomorphisms that maps G onto this twisted product. And what we can see is that this, with this law here, we get, in fact, a group homomorphism, and which is then an isomorphism, because we have a bijection, and the 1 automorphism are, in fact, isomorphic now to this group here, which, putting it together with what we had before, we finally have a decomposition for the cases, at least for the cases of K automorphisms and K stable automorphisms of our groups in terms where only automorphism groups and homomorphism groups of the valuation invariants appear. Now, this bit here is, from a computational point of view, it is not particularly helpful, right? It doesn't help you a lot when you want to have a homomorphism and see how it acts. But it gives a theoretical presentation, at least of this group, in terms of this valuation invariance. And I put the slides in a bit in the wrong order here. This gives a generalization of something that has been done between the lines in a paper of Schilling from 1944, where he does precisely what I was suggesting for the case of Laurent series, where in fact he can use substitutions, right? So he can describe, he can notices that a valuation preserving K automorphism of the Laurent series is always given by a substitution, substituting T by a suitable unit. And using that, he defines an operation similar to the one, analog to the one that we defined. Actually, it's a special case then of the operation that we defined above, and he shows that the group of automorphism is isomorphic to the group of units under this special operation, right? He has all the units because he does it all together. We split it. We have some units hidden. Some units are hidden here because they are the constant part of the unit, and some units are hidden there, which is the 1 unit part of the unit, so the one that has a tail and 1 is first coefficient. Right. So this is this is the main theorem that I wanted to show, and then as a just to show you a few application thereof. So this is a special case that we get if we take G to be a discrete group, essentially, so a product of a lexicographic product of finitely many copies of Z, so a finitely generated group, and applying those results. There is some notation here that I haven't explained. For example, here we have the fact that the group of order-preserving automorphisms of G is isomorphic to the group of n times n upper unit triangular matrices with entries from Z. The homomorphisms of G of z to the n into k star is just k star to the n. And this is what you get via that copying isomorphism technique that I showed before. And downstairs is the analog from which you retrieve Schilling's result. Then another quick application that I want to show, it's a bit of a toy application that hides a dream project for the future, so to speak. So we can look at the Cremona group, right? The Cremona group is an important object in algebraic geometry, and essentially CRN is nothing but the k automorphisms of k x1 xn, right? Of function field in n variables, and which for us is a case. For us is a case like this, right? K is the minimal Hahn field where we take G to be Zn, right? Now in dimension 1, the Cremona group, which is this automorphism group there, is known to be the group of projective general linear matrices, which is invertible 2x2 matrices modulo scalar transformations, and right, determined in this way. So an element of that group is determined by a matrix of this form, and we can identify inside this group the valuation preserving automorphisms and the one automorphism, right? So we can describe in terms of these matrices, or which of these matrices correspond to valuation preserving automorphism, namely the triangular ones, and the one automorphism instead corresponds to the again triangular one with constant diagonal, which also means unitriangular in a sense, because we are going up to scalar multiplication. So and because these are known to be non-normal inside the group of matrices, this gives an example of a non-normal subgroup of the Cremona group. Again, it's in dimension 1, where the Cremona group is in general well known, but in higher dimension, Cremona group is highly unknown. It's highly mysterious. I don't know much about it, but already this, so that's why it's a dream project for the future. Maybe we can extend this idea, and for general minimal Hahn fields for arbitrary n, and maybe find interesting subgroups of Cremona group, which might provide a contribution to the study of the subject. And in the last minute that I have, I will show you the last slide, which is again, it's nothing, it's again an application very similar to this one that I just showed you. Everything looks very symmetric in that sense. Here I am just moving from Z to the D to Q to the D. And again, I get more or less the same decomposition that I got before, except that instead of having upper unitriangular, I have upper positive triangular matrices on this side. And this description of O-aught of the order preserving automorphism, the last on the right, that is also part of what I've done in my PhD thesis. Here in particular, we are extending results of Conrad, partly of Trost and Goebel, on Hahn groups instead, right? But those are not the topic for today, and actually this is exactly the right time where I should stop. So thank you very much. And
just have a curiosity. What's the relation between the automorphisms and the derivations? Because usually for power series, you get automorphism by taking the exponential of the derivations. Right. So here, that's the relation between
by taking exponentials of the derivation.
Exponential of a derivation gives you an automorphism.
Okay, that is something I do not know about, and
But I can comment because
Yeah.
first you have to define the derivations. In order to do this interesting approach, you first have to have the derivations on the Hahn fields. And that is an ongoing project with Matusinski and Berarducci and Montova. So you might hear more about this on Thursday, tomorrow.
You can go the other way around, because when you have an automorphism, you can take the logarithm, form a logarithm with the automorphism, and you get a derivation.
yeah, I mean, I guess you're right. So there are people here which are much more expert than me on this, and I'm not the right person to talk about this. Unfortunately, I'm sorry about that.
Other questions?
Does the case of the field of formal power series in several variables fall into the case you treated? Because this would be maybe an interesting case.
So in a sense, yes. I mean, you can look at something like this as a field of power series in several variables, right? Where each copy of Z is a different variable, for example, right? So those are formal power series in several variables, if you want. So yes, so the answer is yes. I mean, because the group is general, right? So you can.
This one is much larger.
Right. Okay. Okay. So yes, it would. Yeah. Okay. It's a subfield thereof, and yeah, again, because we are looking at subfields, right?
Yeah,
General
yes.
subfield of Hahn field. So that would give you the whole field, right? But the one you're talking about is a subfield thereof,
Yes.
and
No,
all that I've said until now applies to all the subfields, right? All the immediate extensions. Yes. So yeah.
Okay. So this might be interesting to get more explicit.
Right. Okay. Okay. Yeah. Good
Right.
point. Sure. So that is in fact okay. I see your point now. Okay, you are proposing a concrete subfield of that one can look at to get concrete
Indeed.
examples. Yes, absolutely. Sure. Thanks.
Thank you.
Other questions?
I would just like to comment. So the specific subfield is the minimum Hahn field over the lexicographic product of Z, n copies of Z. That was the
Not the rational fraction, I would say the fraction field of the power series.
yeah. That is.
It's a strict subfield. Yeah.
So I have a question. Sorry, last one. So in your decomposition theorem, let's say the second layer one, can you just say it for me?
Yeah.
So in order to, let's say the first line, right, is, or in order to complete the project, you still need, so you did manage to describe the one odd factor
Mhm.
by the homomorphism of G into the 1 unit.
Yeah.
But can you describe more the last factor?
Most likely, yes, I think so. So again, like I mentioned briefly before, that was, so the last factor is in the same way as our Hahn fields by Kaplansky theorems are prototypes for all valued field. Those groups that appear there by an analogous theorem of Hahn, they are all Hahn groups, right? What are called Hahn groups. And it was also part of my PhD thesis to study automorphisms of Hahn groups. Now I've done the same approach, studying rather the valuation preserving automorphism thereof. Here I need to get deeper into the order preserving automorphisms of Hahn group, because those are the ones that appear in here. And yes, so there is a parallel, well, not really parallel, and follow-up project going on where we want to apply analogous approaches to Hahn groups, really in order to describe then this group here, those groups there, and then we would like there to appear the valuation invariance of the group itself, right? Which means the skeleton, the value set, and so on. So that is what we are going to do. And an example was the one that I showed, where you can, by methods of that sort, describe those in special case as matrix groups, for example. That was initiated by Conrad, and yeah.
And also, if you go to the twisted multiplication that you define on Hahn,
Yeah. That one? Yeah.
I was curious, why do you call it times S? Why the S?
Yeah, the S comes from the fact that it generalizes Schilling. The S is the Schilling S.
Ah, okay.
The S comes from this one. Yeah. I don't know, German speakers probably would like me to put SCH as an initial of Schilling. I don't know, but that's too much. So I just put S.